Okay, so the last presentation is going to be about scaling your deep learning models with model parallelism. Um, and I will say, unless you really need model parallelism, you shouldn't be using it. You should try to use data parallelism as much as you can because it's very easy to implement and you can kind of get away with a lot of things with just data parallel training. But at least today we know that your data set is really big and your models are really big, then they can lead to better accuracy of your models and generalization performance. And that's why people are building like these two-learn parameter language models and even more. But the problem is that there's limited memory on the GPU and that creates a bottleneck. Essentially, if your models are really big due to the weights or activation maps, then this can really overflow your GPU memory. And the bottom line is that at some point, you're going to saturate your data parallelism. Even like having a single local batch size of 1 is no longer going to fit on your GPU. And you're going to have to resort to alternative techniques to parallelize your model. I will say there are some very quick strategies that you can use to reduce the memory already without going to model parallelism. And this is like activation checkpointing is what a lot of people suggest. That basically means you don't store any memory for the backward pass on the GPU, but you keep recomputing it. You typically pay a lot of computational costs to do this, which is why for the really big models, you would have to go to model parallelism. So for really large models, we have to partition or shard the model itself across multiple GPUs. And this is the realm of model parallelism. And the idea here is you break your model up, you perform some local computations, and you communicate the results. And in this presentation, we're going to show you how to do that with this specific model. And then in the hands-on, you will actually be able to run training code with a much larger vision transformer. So in order to understand how model parallelism works, it's good to think about your deep learning model as just a series of weights and activations that are represented as multidimensional tensors. So here, I've kind of colored the weights as this orange color, roughly like m cross n, let's say, and your activations in this blue color. So in our case, once again, activations is you have a batch of them, you have a sequence length L, that's your entire spatial dimension, and an embedding dimension, which is your high dimensional space in which we're learning. And then basically this is kind of repeated over many, many layers. Parallelizing your deep learning model just means you as a user is deciding which of these tensor shapes you're going to split across multiple GPUs. So for example, in data parallelism, you're just splitting the batch across multiple GPUs. In pipeline parallelism, you're actually sharding the depth. So some layers are kept on one GPU, the other layers are kept on another GPU. We're going to be focusing on tensor operator parallel here, because this is actually the most useful for this model. Any other dimension that you choose to shard, like in the weights or an activation, this is called operator parallelism. Technically, data parallelism is also very similar to operator parallelism because you're just sharding the batch dimension, but usually people split it up because data parallelism is so easy to implement that for some reason this hierarchy exists today. Okay, so let's do that with this vision transformer. So once again, the vision transformer is self-attention MLP blocks that's repeated. I showed this to you yesterday, but you have a tensor shape that's going into self-attention, comes out, goes into MLP, and then comes out again. So if you understand how to parallelize the MLP, then pretty much know how to parallelize the self-attention as well. So let's do that. So what is the MLP layer? It's just a bunch of matrix multiplies. In fact, everything in the deep learning model is a bunch of matrix multiplies. You have your input tensor, batch LE. You're multiplying it by a weight matrix. Once again, weight matrices are colored in orange. So you typically have something like E cross F. In our case, F is 4 times E. That's because typically transformers lift to a higher dimensional space that's roughly like 4 times bigger. So this matrix ends up being like this fat matrix. You multiply these two tensors, you get L cross F. I'm kind of dropping the batch dimension here because it makes it easier to visualize. You have some sort of nonlinear activation functions, typically ReLU or GeLU. These are pointwise operations that you're doing. And then this is multiplied by F plus E to bring it back to L plus E. So F plus E ends up being like a tall and thin matrix. In model parallelism, what you want to do is parallelize this entire operation. So remember that you've already done data parallelism by just splitting up the batch dimension. Now we're going to start splitting up other dimensions because your model is that big. So what people typically do, and this is where you start off, is you take your weight matrix and you start splitting it up into multiple GPUs. So here I've taken 4 GPUs as an example. So GPU 0 is going to hold just one partition of your weight matrix. In this case, it's E comma F by 4. So M is equal to 4 here. So that's what GPU 0 is going to hold. GPU 1 is going to hold this shard, GPU 2 shard, and then GPU 3 is going to use the last, is going to hold the last shard. Okay, so already you can see a memory reduction for the weights as your total memory of your weights divided by 4, because every GPU is only holding a smaller partition of your weight matrix. And now you can do your matrix multiply. So you're trying to do an L cross E matrix multiplied by an E cross F by 4. The result is going to be L cross F by 4. You've actually already done parallelizing this layer because everything that you need for this matrix multiply already exists for you on your local GPU. Yeah, why is that? Because the way matrix multiply works is you take a row of your first input matrix, you take a column of your second input matrix, and you compute the dot product. So clearly for any entry in the final matrix, you have the full row and you have the full column on your local GPU. So your parallelized matrix multiply is already done. And then note that your final activation is also automatically split into different shards. So each GPU is only computing its local shard, which means you should also see a memory reduction for this activation. Okay, let's go to the second matrix multiply. So you now have L cross F by 4, and you're trying to multiply it with that tall and thin matrix. Once again, your weights are now sharded across multiple GPUs. So GPU 0 contains like this shard right at the top, and so on for the other GPUs. Okay. So now when you want to compute your local matrix multiply, you actually don't get a final result. You really get a partial sum. That's because you really have a part of the row of this matrix and a part of the column of this matrix. The other rows, the other parts exist on other GPUs. So when you actually do the dot product, you're really computing partial sums. So at this point, you need to do a communication collective, an all reduce operation to actually sync your results. This is very similar to data parallelism. In that case, your batch dimension was sharded, so you had to do an all reduce for the gradients. So in tensor parallelism, you have an L cross E partial sum that you're going to have to do an all reduce across your tensor parallel GPUs to get the final result. The general rule of thumb here is if you're doing a matrix multiply and your inner dimension is sharded, then you need a communication collective. So what does that mean? So for example, here, my inner dimension is the second dimension here and the first dimension here. That dimension is sharded. This is the contracted dimension, which means I'm going to need to call a communication collective, and in this case, all reduced to sync the results. This is once again true again for data parallelism because your inner dimension there turns out to be the batch dimension, which is why you do an all reduce across your batches to compute the synced gradients. So at this point, we've actually completely parallelized the forward pass of your MLP layer. This is the most confusing part that people usually forget about, is that you need to think about the backward pass as well. The good news is that the backward pass is always like a conjugate operation, which means it's actually very easy to think about what's going on there. So just to recollect how the backward pass works, you have, let's say you have a layer that's taking your input activation, multiplying the weights to get Y. So in this case, that was L cross E, and your weights were sharded, and you get this activation. Your inner dimension is not sharded, so that E dimension is present on every GPU. Everything good, no communication here. Your backward pass is going to look like gradient of the loss with respect to X is basically gradient of the loss with respect to Y times W transpose. So this is just chain rule. This is how backpropagation works. So if you think about what the gradient of the loss with respect to X is, it's going to take a look at a tensor that's batch times L times F, in this case, F by M, because it's sharded on multiple GPUs. And you're multiplying it by weight matrix transpose. So that was your weights. It's now transposed. So you have F by M comma E. So now your inner dimension is now sharded for the backward pass, which means you need an all reduced communication collective here to actually sync the gradients. But like I said, the backward pass is always the conjugate operation. If your forward pass doesn't have communication, your backward pass would have to all reduce. If your forward pass has to all reduce, your backward pass will not have any communication. So this is how it generally works throughout the transformer layer. And once you've done this, you're basically done in tensor parallelizing your MLP layer. In order to what to expect, once you tensor parallelize, sharding will reduce your activation memory footprint. Like I said, these activations now, only a small partition of them lives on each GPU. So if I just count the memory that I need, I would need to store this activation, and the final result. So in the example that we have in the code, let's say our batch size was 16, sequence length was like 1450, embedding dimension 1024. Without sharding, I would have needed about 1500 megabytes just to store the activation memory for this one MLP layer. But after sharding, that should drop to around 800 megabytes. So this is the kind of memory savings that you would expect by doing tensor parallelization for this layer. What about the weights? Instead of having E class F, you're now going to have E class F by M, and the second weight is F by M class E. So without sharding, you would have to use like 30 megabytes, and with sharding, that would drop to like 8. This is really important. Note that different parts of the model are seeing different memory reductions. The specific model here actually uses a lot of memory in the activation maps and not the weights itself, which is why we're seeing a lot more savings in the activation memory. But either way, when you look at NVIDIA SMI on the GPU, you should see the total memory come down. Sharding also reduces computational costs. So there's two reasons to do model parallelism. You want to fit things on a GPU, but also since you have more GPUs, things should go faster. So if you think about how to compute that, the total flops of a matrix multiplier, you can actually analytically compute them. That will get reduced from, let's say, 1,000 gigaflops to 270. So everything should be going faster as well. So all this sounds great. So things are going faster. You're saving on memory, but of course, nothing comes for free. You're now paying some costs and communication with this all reduce. And in this case, you're always communicating a tensor of shape batch times L times E across your network. To get a sense of how long that will take, that's basically your communication volume. So that's about 260 megabytes that needs to go across your network. So you just take volume by the bandwidth of the network to understand how long it will take to communicate with it. So this is the cost that you've paid in order to do model parallels. Okay. So now that we have like a very high level understanding of what we want to do, let's try to understand how do we actually do this in PyTorch. We're going to go in like a top-down fashion. So we're going to start with the vision transformer definition. So normally you would have called into like an MLP layer, but now in the code, you'll see that we've called into a distributed MLP layer if this TP stands for tensor parallelism is greater than 1. So now I'm saying as a user, I want to use more GPUs just to do tensor parallelization. So I'm going to call into this distributed MLP layer, okay? What is that going to do? So normally within your MLP, you would have written something like, my layer is nn.linear of input features, comma, hidden features. In this case, input features is E, hidden features is F, equal to 4 times E. That's what you've written normally. But now we're going to call into a distributed matrix multiplier that we will implement. It's super easy to implement this. All you have to do is define your weight matrix as the local partition of your weights. So normally you would have had your weight matrix that's of size E comma F. Instead, you tell PyTorch it only needs to be E comma F by 4 in this case, or F by M in general. Note that you need to take care of the communications. So we want to implement routines that will do that all reduce for you. So we're going to need two routines, one to implement the all reduce during the forward pass, and one to implement that in the backward pass. So remember that just because your forward pass doesn't have communications doesn't mean everything is good. Your backward pass still might be shorted, and you have to do a communication cost. So in the code, the way we do it is we have these two function calls. It's called copy to parallel region and reduce from parallel region. That's pretty much going to do this. So it's going to implement these all reduce functions either in the forward pass or in the backward pass, so that you can tell PyTorch that you're doing a distributed matrix multiply. Okay. So just to reinforce, your first routine that's copied to parallel region should look something like do nothing in the forward pass, just take your input, return the input. But in the backward pass, it needs to do an all reduce because as we're coming back with back propagation, things might be sharded, you want to do a backward pass. The second routine is exactly the reverse. It needs to do the all reduce in the forward pass, and then it's an identity operation in the backward pass. Okay, how do we do that in PyTorch? The great thing is if you go to the PyTorch talks, they'll tell you exactly how to do this. It's called using custom autograd functions. Any function that the user wants to implement that does not have a backward pass already automatically implemented, PyTorch recommends that you use custom autograd functions. It's very simple. All you have to do is inherit from this torch.autograd.function class and tell PyTorch, what should I do in the forward pass? What should I do in the backward pass? So in this reduce from parallel region, the forward pass is going to do a reduction of the input. The backward pass is going to do nothing. It's going to pass the gradients just without touching it. The other function is just going to get reversed. In the forward pass is going to do nothing. It's just going to take that input, going to return the input. The backward pass is going to do the gradient. And that's it. So once you have this implemented, your entire MLP layer is now tensor parallelized. If you want to go to self-attention, the good news is everything that you implemented for MLPs kind of directly translates because everything is matrix multiplies, and self-attention as well. I went over this yesterday, but just to recollect, what the self-attention will do is it will take your input vector and project into these query key values. The way that's done is you take your input tensor, multiply it by this weight matrix. It's done in one shot. Like you see that each Q cross 3. The 3 is because it's creating queries, keys, values in one shot. And then there's like a self-attention operation. I'm not going to spend too much time here. I left it in the slide so that you can go back and see what's going on. And then you'll have like a projection operation. The amazing thing about the self-attention for tensor parallelization is that you typically have multiple heads. That's what H stands for. That's doing the self-attention in parallel, which means if one head was on GPU 1, the second one was GPU 2, it's embarrassingly parallel. So all you have to tell PyTorch is don't use all the 32 heads. Just define maybe 8 heads per GPU, and you've already parallelized the self-attention operation. That's like one single line of code. And for these, you've already implemented distributed matrix multiplies. So you just call in that function with the right tensor shapes, and you should, and the self-attention also gets parallelized. Okay. I'm going to skip this, but it's the exact same thing I said before. You might not have to do anything in the forward pass, but in the maybe if your inner dimension is sharded, you need to have an all reduce function. Same logic. There is one extra thing in self-attention that is generally glossed over because this is kind of like the default that people use, but I do want to kind of emphasize that this is also important. There is a concept called flash attention that PyTorch generally recommends that you do. The idea is very simple. If I actually do this full attention computation, I'm going to end up with an attention matrix that's going to look like batch, comma, number of heads, comma, sequence length times sequence length. If my sequence length is really big, let's say I had like 1 million tokens in the sequence, this matrix is going to be a 1,000,000 by 1,000,000 matrix, which is just incredibly huge to store on a GPU. So if we take even our example, let's say L was just 4050, storing this matrix is 8 gigabytes for just a single layer, which is really big. What flash attention does is it says, forget about storing this matrix. I will just recompute this during the backward pass as and when I need it, so that you don't see this huge GPU memory utilization. Flash attention is switched on by default in our code base, but in the hands-on, I'll show you where you can switch it off, so you can actually see things explode. Generally, we do recommend that you keep flash attention on. It's a simple call to PyTorch's dot product attention function, and by default, that implements flash attention. Okay, I'm going to skip this. Okay, how do I implement distributed attention in PyTorch? As I said, it's if I've already implemented the MLP, This is fairly straightforward. I just tell the attention layer that the number of heads locally on my GPU is the total number of heads divided by my number of GPUs used to partition. So that part is already done. For the projection matrices like QKV and the projection, instead of calling nn.linear, I'm going to call distributed mathmod that we just implemented. Okay, and this would complete the tensor parallelization for the attention operations. Okay, so now we know that we know exactly how to do tensor parallelization to this entire model. It's important to understand that usually people just don't do model parallelism. They're always doing it in addition to data parallelism. So you would first do data parallelism in case your models become so big, then you're going to add additional GPUs to the model parallelism. So typically how that's done is you have data parallelism that's done orthogonally to model parallelism. So you can think of, let's say I had like 64 GPUs and I had done, let's say 16-way data parallelism before and it didn't fit. So I'm going to use maybe 4 extra GPUs to do model parallelism. My total number of GPUs becomes like 4 times 64, so I have 64 GPUs. And the idea is to use like D instances for data parallel and M instances for model parallel. This is a very simple example. So let's say I had just 8 GPUs in total. And as a user, I decide that I'm going to need at least 4 GPUs to do model parallel because the model is that big. So I'm going to assign 4 GPUs to do tensor parallelization. I'm going to do the rest 2 data parallel instances. So what that means is my global batch size is getting split twice because my data parallelism is 2. So one local batch comes to this group, another local batch comes to this group. Again, remember that in data parallelism, your model is replicated. So each of these data parallel groups has the same model. But within these groups, we're going to use 4 GPUs to actually split the model apart. So if I'm in group 1, then my model is actually sharded across 4 GPUs. That's where all of your weight matrix is kind of split up. And we do exactly the same thing for this. Okay. How do I tell PyTorch to do this? Again, if you go to the PyTorch talks, they tell you exactly what to do. But the idea is you just use torch.distributed and tell PyTorch that I'm creating groups of GPUs. So I'm going to create data parallel groups. I'm going to create model parallel groups. Understanding where to put the GPUs is kind of very dependent on what your communication costs are. And we recommend that you optimize your layout of GPUs according to the communication density. So for data parallelism, we do have a communication collective that's all reduced over the batch dimension. But what DDP does automatically for you is it overlap all of this with compute. So you might not even see that communication costs. But for model parallelism, especially tensor parallelism, those collective communications kind of occur on the critical path. You need to do that all reduced to get the right answer. So which means you're very, very bandwidth dependent. So what people generally recommend is you do your model parallelism within some island where you have high bandwidth. An example here is specifically for core model. So on core model, you will know that every node is interconnected with NVLink, which actually gives you a much higher bandwidth than inter-node bandwidth. So we kind of recommend that you do all your model parallelism within a single node, and then you use your data parallelism across nodes. The last thing that you have to be careful about is that by default, your data parallelism data loader thing will assume that it needs to split the data up equal to the number of GPUs that you used. But you need to tell that sampler to not use that and just tell it how many data parallel groups is there. So in the previous example, for example, I need to tell the data loader that there's only 2 data parallel groups, so I just need to split my batch twice. So in the code, you will see something that's called data num shards and data shard ID, and that's basically telling the data loader that use the size of your data parallel group to actually split the data. Okay. So if you're still not satisfied with this because your model is just that big, this is basically typically done for those student parameter language models that you see. You can do something called pipeline parallelism and context parallelism. I would say pipeline parallelism is very useful if your weight matrices are huge, like student parameter LLMs. And that's so you can just split up your layers onto multiple GPUs. This is not a distributed matrix multiply problem, but more of a scheduling problem. We're not going to go into pipeline parallelism today because it's not going to help us a lot. Because in our case, what's more important is the activation memory. As I showed you before, most of our memory is actually going into the activation maps. And that's because we're dealing with very high resolution images, which makes that sequence length really huge. So what people recommend is something called context parallelism. This is done for LLMs as well, for LLMs with really large context windows. And then what you can do is you can take another group of GPUs called context parallel GPUs. So you have M cross D cross context parallel number of GPUs to shard just the sequence length specifically to fit the model. So you're now looking at 3D parallelism. In language models, like the biggest, let's say the latest Llama models, they have huge weight matrices, really large context window. So they actually do M cross D cross context parallel times pipeline parallel. So it's four-dimensional parallelism. And for the really state-of-the-art models, they have like mixture of experts, and they actually do 5D parallelism, where they do expert parallelism as well. So but we're not going to go into any of that today because that's just crazy. But the idea is that pipelining is even less sensitive to communications. So you typically pipeline across nodes. Once again, you don't want to keep your pipeline parallel GPUs within the same node. In the code, we do implement context parallel for you guys so that if you're really interested, you can actually see how we've done it. And in the hands-on, you will get a chance to run context parallel as well and see what the differences are. But I will say that that's really not required. Maybe after the training, you can feel free to kind of submit those jobs. Everything in our code is based on Megatron LM. This is a open source code base from NVIDIA for training their flagship language models. Any code that you see in our code base, you can also find it somewhere very deep inside Megatron. But there are other resources that are pretty useful. DeepSpeed is from Microsoft, that also does very similar things. NeMo is an additional layer on top of Megatron that NVIDIA recommends for training very specifically language models. And then there's Colossal AI and Hugging Face also, which also implement model parallelism. But hopefully the tutorial code is good enough for you to understand what's going on. And if you're really interested in going deeper, then these resources would be a good starting point. Okay, so that completes my presentation. Are there any questions?
Context parallelism and pipeline parallelism are forms of model parallelism.
Yes, yeah. But again, you would only need to do that if you really want to. And the pipelining will not help you too much in our example because our context length is huge and our weight matrices aren't that big. So the context parallelism is what is probably more important. I should actually link another repository here from NVIDIA called Modulus. That's very specifically for scientific machine learning. But they also implement very similar things. They call it spatial parallelism. They pretty much do spatial parallelism for their like, really big models. Any other questions?
Is there a general way to balance the computational cost and the computation cost?
Okay, so it's pretty hard because you have like multiple dimensions and the costs are generally competing. You typically have to do some sort of performance modeling to understand how much is your computational cost, how much is your communication cost, and where it gets balanced. A lot of industry teams will do it by hand. They will build a performance model of their deep learning model to understand where the costs are and then figure out how to optimally parallelize the model. But I think, for example, if you look at Colossal AI, they will build something called auto parallel tools, where they kind of build a solver that will search through all of your configurations and automatically figure out, okay, given 1,000 GPUs, how should I split it up into data parallels, etc.
Hi, Shashank. So I have a question. Maybe I missed. Can we do data parallel and model parallel at the same time? Will we do it today?
Yes, yeah, you will be doing it at the same time. The logic is that you're going to assume that you have M cross D array of GPUs, where D is your data parallel instances and M is model parallel instances. And in the hands-on section, we will be doing both simultaneously.
Okay, okay, thank you.
And in general, you want to, like I said, you don't want to be doing model parallelism without applying data parallelism first. So it's usually stacked one on top of the other.